Thank you, Max. Thanks, the organizers, for the invitation. I'm going to talk about a topic that is non-local, but not in the sense of materials. It's in the sense of developing numerical methods. It's joint work with Wujun Shang, that was a postdoc in Maryland until about a year ago, and these two people, Dimitris and Wenbo, that are students in Maryland. So I'm going to present a Maryland product. This is very strange. Sorry, but okay. Here is the outline. So I'll motivate the problem, and I will focus on this, which is a topic of intrinsic interest in some sense. You will see what it means, and then talk about the 3 examples of two-scale problems. Okay. So the driving issue behind this research is to be able to do finite elements, perhaps not in the way we are used to, integration by parts, which are well designed for variational problems, on problems that do not have variational structure. Still, finite elements offer flexibility in terms of geometry, in terms of functions that we can use, as opposed to more standard finite difference methods that typically are designed on structure meshes. So for instance, approximations of domains and so on. So the idea is, I'm going to give you a few examples of what I mean. The first one is Monge-Ampere. It's a problem that is well known in many areas. It appears in geometry, optimal transportation, nonlinear elasticity, even designing good meshing techniques. And it's basically looking for a function u that is convex, whose Hessian has a property that the determinant is a given function. So since I'm looking for functions that are convex, the right-hand side has to be non-negative. In most of his talk, it will be strictly positive. This is a very difficult question, a very difficult equation to approximate, and it has no variational structure, as you can see. At least not obvious. The second example is that this equation, so-called Bellman equation, appears in control, where you have an equation like this linear in non-divergence form, actually a set of equations parameterized by alpha, and you look for a sup. And in order to do this, you probably want to know how to deal with this, which is one of the ingredients. Is again the same equation, now without parameter. It's a non-divergence form. And the key is what I'm assuming about these coefficients. The coefficients are going to be bounded, positive definite, but I don't want to assume much regularity of these coefficients. In fact, I see here vanishing mean oscillation will be a typical assumption, but I'm not going to insist on that. So for instance, a typical assumption will be the coefficients are uniformly continuous. But they will not be Lipschitz, so I cannot transform the equation by integration by parts in divergence form. And I cannot use the obvious approach with finite elements. I will assume more later for convergence. And the last example is computing the convex envelope, which is in the family of problems. It's interesting. And it's the following. You have a given function f, let's say Lipschitz, or even more regular, and you want to construct something that is here in red, that is, as you see, the sup. You touch from below with affine functions, and you take the sup. What you get, which I call gamma of f for later, or in this case u, so given f I want u, that is convex, not necessarily strictly convex, and it touches the function from below. Okay? The question is how to formulate this problem in a way that we can compute the convex envelope, and this PDE is due to Oberman in 2007. So it's an obstacle problem, but for a fully nonlinear equation. So you want u to be less or equal f, and when u, like in this case, is strictly less than f, and this is negative, you want the solution to be flat. Which means, since it's going to be not positive semi-definite, the Hessian is going to be positive semi-definite because we are looking for a convex u. We want the minimum eigenvalue, which I call lambda of the Hessian, to be 0. So this is a typical obstacle problem. This is non-negative, this is non-positive, this is non-positive, but we want one of them to be positive. So this is a complementarity relation. I will come back to that. So that's the equation we are going to approximate. And here you have a list of authors that work on these topics. There are many contributions, but not so many. In fact, this is an emerging area. So I will not insist. Let me just say a couple of words. This is a summary that is very recent about fully nonlinear equations. It's an interesting contribution. About Monge-Ampere, there are different approaches you can see here. None of them like the one I'm going to present. I'm going to focus on pointwise estimates. What I'm going to present differs also from the original work by Oberman. And regarding elliptic equations in non-divergence form, here you have some contributions. I think this is the last one is particularly interesting, but different from what I'm going to discuss. So let's get to the first topic of the talk, which is the Alexandrov maximum principle. I'm not assuming that this is you are familiar with these things. This is an important tool, a key tool in the theory of fully nonlinear equations. And since one of the goals that I have is to deal with fully nonlinear equations and come up with a numerical method, it's very natural to have at our disposal a tool to study them at the discrete level, which is sort of a parallel, mimics the main tool at the continuous level. So here is the situation. Suppose you have a function, which I'm calling here W, and gamma of W is a convex envelope, exactly what I defined earlier. Okay, it's a convex function, the largest convex function that lies below W. So you are touching from below with affine functions, and you take the sup. Now I'm going to use this gamma of W as an instrument for analysis now. I'm not going to compute it. I'm going to use it as an instrument. So let me introduce a few notions. Where the two functions coincide, like in this area, this set I'm going to call contact set. Is a region where the function and the convex envelope coincide. Now here is the estimate, which is called Alexandrov. So you want to look at how much the function W can go down. The function has 0 boundary values, so you want to look at the mean. Okay, in order to express it, I take the negative part, which I define it to be positive, and I want to look at the sup. Okay, so I'm looking at how much a function can go down. The function can have a lot of structure, but if it goes down, the mean is dictated by the region where the function is convex, and in fact it goes down. It doesn't matter this part. So what this says is that if you want to control this value, basically you need to control the determinant of the Hessian of the convex envelope, and only in the region where the two functions coincide. So it will be on this function, on this area. So in this area, the two functions coincide, and that determinant of the Hessian is what dictates. Notice that this is integrated in L1, even though we are here computing the max. So there is a mix of norms, which will be useful for later. Okay, I hope the geometry is clear. It's only the convex part, which is where the convex envelope and the function coincide, that determines how deep the function can go. Since I'm interested in infinity estimates or pointwise estimates, this will be an instrument. But you can think that the W for me will be an error, discrete error at some point, and I will have to deal with the convex envelope of the error and try to relate that to the equation. That's sort of what is in the background. But the equations that I have are typically nonlinear. So let me rewrite this. I want to rewrite this in a way that is useful for problems where the W is not smooth. So see, when I'm writing this, I'm implicitly assuming that I can write the Hessian. If the function is not smooth, it has a corner, for instance, a kink, then I had to give an interpretation of this. Since I want to go to piecewise linear functions, this is the ultimate goal, this W will be a piecewise linear function. And then you immediately see that there is a problem. A piecewise linear function is flat in an element, in which case the Hessian is 0, or it has a kink when you cross elements, in which case the Hessian is singular. So what do I mean by this? Okay, that's the next step. And it's just to interpret the gradient map. So suppose that I have omega, I compute the gradient of W, and I get the image of that map. So the Hessian of W is the differential of the map, or the gradient of the map, if you like. So at least formally, if the whole thing is smooth, the integral of the determinant is the area. So let's say that I compute the integral of the determinant of S. S is a subdomain here. It's just, by change of variables, the area of the image of that subdomain by the gradient of W. Okay? Assuming everything is smooth. Now, if I want to write here the determinant of the convex envelope, which is what I had before, okay? Instead of that, I can replace it by this. Okay, by the measure of the gradient, well, that's the sub-differential of the convex envelope, and it's computed, this is the S that I'm dealing with, the S is just the contact set, okay? So that's basically reinterpreting the formula in a way that I'm able now to give meaning when this is less smooth. I just need to be able to speak about the sub-differential of a convex function. Doesn't have to be smooth. Okay. Now what happens if I have a piecewise linear function? Well, imagine a piecewise linear function. For the moment, let's focus on this picture here. So imagine that you have a hat function, and I put it upside down. Okay? So the peak is pointing down. It's a convex function. I want to understand the sub-differential. So what does it mean? Well, here's a definition, a formal definition of a sub-differential. I call this function little gamma as an abbreviation for capital gamma of WH. Okay? So again, imagine that you have in 2 dimensions, in 1 dimension is clear, you have something like this. So you touch from below, and with a plane that is below the function. All these lobes belong to the sub-differential. That's the definition of sub-differential. Now you are in 2 dimensions, okay? If you are in 2 dimensions, like here, this is a star of a patch associated to a node. So imagine that you have these 2 triangles, okay? So you move your plane that is going from below and touch one of the sides. In that case, the vector is the gradient. You can move down and touch the other side. So now your vector in the sub-differential is the other gradient. So you have one gradient, you have the other gradient. Okay? Now you have these two sides of the hat function. You can touch one side, you can touch the other side. Now you can touch the edge in common and move the plane like this until you touch one side or you touch the other side. And that, in this picture, is going from one gradient to the other, connecting this. Then you can repeat that for all the sides. Okay? And what you get, you can think about it, is this convex set. This is a polygon. There is a convex hull of all these piecewise constant gradients. That's a sub-differential of a convex piecewise linear function. Okay? And what is important in this formula, you see, is the area. Now the area of this set can be computed by simply taking the length of the sides, of the perimeter. This is an isoparametric inequality. The area of a set can be determined, can be estimated by the perimeter. So if I want to compute the area, I can simply compute the perimeter, but you see the perimeter is the length of this size is the difference of the gradients. The difference of the gradients are what we call jumps in finite element theory. So jumps are critical for the sub-differential. They will enter. We are used to these things because of DG or because of a posteriori error analysis, but if I want to deal with the convex envelope, and the sub-differential, they are also natural. Okay. Now, here is a discrete Alexandrov estimate. And here is the what I mentioned before. This is the way I wrote it before, the continuous one. We computed the sub-differential of the convex envelope over the contact set. That's what I told you before. And that was assuming that the W maybe was smooth. So what is the counterpart? Well, you have the sup of a piecewise linear function, the negative part, and this is, you look at each of the nodes that are in the contact set. By contact set, at the discrete level, I mean nodes where the function piecewise linear WH and the convex envelope, which is also piecewise linear, coincide. So the contact set is a collection of nodes. Okay? Of course, you can think you can have a piecewise linear function and the convex envelope may touch a whole face, in which case it will touch all the nodes of that face. I don't care what happens inside, I'm counting only nodes. And that's what I'm doing here, I'm summing over nodes the areas of the sub-differential. So I had to add all of these quantities, which I'm going to replace by the length of the perimeter. Okay? So this is the counterpart of this. This has to be proved, but it's believable, I hope. And here is what I mentioned. These are the jumps of the gradient defined on edges, the edge of faces, I call F for faces. And here is a connection with the discrete Laplacian. So the discrete Laplacian is this object. Notice that I didn't write minus here, so I had to write the minus in the bilinear form. So phi's are the usual hat functions. Okay? At a node I, xi, they are 1, 0 otherwise. So this is the definition of discrete Laplacian. If I integrate here by parts over the WH, I get the jumps. These are things that we know from a posteriori analysis of DG. The jumps are written here, are piecewise constants. And this guy is piecewise linear, so we can integrate this over an edge, over a side. Okay, and what we get is the area divided of the face divided by the volume. The volume comes from here, and there is some scaling that has to do with the dimension. So you can see that the discrete Laplacian has to do with sum of jumps, scale. And if we have a linear function that is piecewise linear, that is convex, these jumps here happen to have a sign. So these quantities here are non-negative. So why do I care about this? Because I want to look at the area of a sub-differential. I will replace that by the perimeter. The perimeter is a sum of jumps, and the jumps are all non-negative. So the sub-differential is related to the discrete Laplacian. Okay? Which is what I wrote here again. The Alexandrov estimate tells me that the amount why the function can go down is related to the discrete Laplacian or nodes that are in the contact set. Okay, so I will use this connection in a moment. All right. So this is all I want to say about the discrete Alexandrov estimate, and I'll use it in two instances. The first one is to design a method for equations in non-divergence form. Okay. So I'm going to use an approach that was introduced in the PDEs by Caffarelli and Silvestri for a completely different reason, but it's very interesting to do it at this level. So I want to approximate this equation. Again, I have a matrix which is positive definite, but it's not smooth, times the Hessian. And I want to do it in the context of finite elements. And I want to assume that the matrix is strictly positive definite, so the smallest eigenvalue is positive. I call the smallest eigenvalue lambda. The matrix cannot degenerate. If the matrix degenerates at a point, this method will break down. So this is a method that is valid for uniformly elliptic problems. Okay? The smallest eigenvalue cannot vanish. So the way I'm doing this is, you see, I added here a Laplacian, but with a scaling delta over 2, and I subtract that. So I didn't change anything. This is the same equation that I have here, but because I put lambda over 2 and the smallest eigenvalue of A is lambda, this is still a positive, strictly positive definite matrix. Okay? So now I'm going to approximate. This is something I know how to treat with finite elements. This is our friend. Now I want to replace this by an integral operator, which I call I epsilon. Epsilon is a scale. This is the second scale of the two-scale problem. The first scale is the mesh size. Now I want to introduce another scale, which I call I epsilon. How do I do that? Here is the I epsilon. And here you see a connection to other ideas that are around. For instance, peridynamics, you see these things. Epsilon is going to be a finite horizon, if you like, in the language of peridynamics. Even though this was introduced for completely different reasons, that I just want to draw a connection. I don't think Caffarelli and Silvestre had peridynamics in mind. I'm not sure at that time it even existed. It did exist? Okay. So delta of U is a symmetric second difference, a center second difference. So X stands for the point where I'm standing, and Y, the point I'm going to add and subtract. So this is symmetric. And Y, you see, I'm going to go away from X by a certain distance. So the horizon, I'm sitting at Y, I'm thinking of a ball, and the radius of a ball is epsilon. It's not quite a ball, because it has to do with the support of this function phi. Phi is a smooth function. I'm going to tell you exactly. It has a support on a ball of radius 1. So if these metrics happen to be the identity, then Y should be less or equal epsilon, and we will have a ball centered at X. But in fact, I have this matrix M, and M has to do with this part of the operator. In fact, this is the square root, which is well defined because this is a positive definite matrix. Okay, and then there is a scaling and so on. So here I have second differences on a scale epsilon, which is larger than h. Is this a good idea? Why this approximates somehow that? Well, let me convince you that there is a merit. Well, before I do that, notice that I have a scale which I call epsilon, okay? This epsilon, which appears here in the denominator, and here, this epsilon is fixed. So the way it's defined, I have problems if I get close to the boundary. If I'm closer than epsilon to the boundary, this ball that I need to, this will go outside the domain. So how do I handle that? I here carefully said suitable modification. I know you may ask me, if not now, after, why I mean by suitable modification. What it means is that I have a ball of radius epsilon, and I move it around, and if I'm close to the boundary, I reduce the epsilon. It's never going to be smaller than h, because I'm dealing with interior nodes. But from epsilon, which is at a larger scale, when I'm get to the boundary, I reduce it to h. And that I had to pay for. So if I'm inside, at a distance larger or equal epsilon, I'm okay. You will see why. I'll show you in a moment. But if I get close to the boundary at a scale smaller than epsilon, then I have a problem. And you will see also why. So I had to deal with the boundary effect. And that will cost me. Okay. So why is this a good idea? Well, to convince you that that's the case, I want to replace u by a quadratic. Okay? By a quadratic function. And see what happens. So if I have a quadratic function, then the second difference, which I wrote here, the symmetric second difference, center second difference, can be written, because it's a quadratic, as this product. The Hessian, which is a constant, because I have a quadratic, multiplied by y times y. Okay, so in the previous formula, in this formula here, I replace this by what I just showed you, and I insert the kernel. Okay, so I have this formula here. Except that because this is constant, I can pull it out. And so now I need to deal with this quantity here. When you do a change of variables, just to get rid of this, I call z this argument, recalculate, and you end up with this expression that you have here, but just by change of variables. The scaling of epsilon to the d plus 2, has to do the 2 with the fact that I want to do is an approximation of second derivative, so I had to divide by the scale square, which is epsilon, and the d here has to do with the integration. So both go away when I do the change of variables, and I get this. And I haven't tell you anything about phi. Now I'm going to decide what phi is. I'm going to take phi to be radially symmetric, such that this is, because of being radially symmetric, this is 0 if I is different from j. And if I is equal to j, then all of these products are the same, and because they are all the same, it's 1 over d times this quantity when I collect them all. And then I impose that this is just equal to d. If I do that, then I get a matrix here, okay, this matrix here, which is the identity. If I get the identity, this is m times m. Remember, m was the square root of this matrix. So now I get m squared, and that is equal to this, and that's exactly what I approximated. So this is a simple calculation that tells you that there is a merit. If a function happens to be quadratic, I have no error. If the function is different from quadratic, the error comes from the next term in a Taylor expansion. So this method is consistent with 0 error for quadratics. And this is what I'm going to be doing. I'm going to be evaluating what happens when I deviate from quadratic and try to put it together to get an error estimate. Okay. First of all, consistency. Well, this is very easy now. If you have a function beyond, it's not necessarily quadratic, but has regularity beyond two derivatives, you can estimate the integral operator and what is supposed to approximate. Everything here is classical. This is defined pointwise by epsilon to the alpha. Alpha is the excess of regularity, and epsilon is the scale. That's believable Taylor expansion. You can go even one order higher. This maybe you want to think about a little bit, but it has to do with symmetry. Because we are doing symmetric differences, then there is a built-in order if you have more regularity. Okay, and you have convergence without rate if the function is just C2. So this is Taylor expansion. This is going to be useful for later. And here is the two-scale method that I anticipated. So let's say VH is a standard space of piecewise linear, continuous piecewise linear, 0 at the boundary. So here is the discrete solution. This is the approximation of the Laplace term. Remember, in case you are concerned with the sign, I put the Laplacian here, no minus the Laplacian. Okay? So that's why I have this term. We are used to this without the minus. This is the Dirichlet form. I'm looking for a function UH that will be in the space, epsilon. So it's a two-scale solution. This is the approximation of the integral operator, and you see it written here. So I have an integral. The integral operator is an integral, and I'm multiplying by a test function. So I have a double integral. This is a problem for what I want to do. So I'm going to do mass lumping, which means that I compute this integral by taking the nodal value of the integral operator multiplied by the mass of the test function. So I go from a double integral to a single integral that is inside here. And so here is the form, if you like, of the operator. I put this together with this. I divide by this quantity. So I get this, which is a discrete Laplacian. You may remember this from what I defined earlier. At the point xi, the integral operator did not change, okay? Is this guy, evaluated at the node. And that has to be equal to fi, which is a mean of f. That's a discrete problem. That problem has a solution, has to do with monotonicity. And here is an instance of that. So we have monotonicity of the integral operator in the sense that if we had two functions, BH and WH, coincide at a node, one is smaller than the other, then the integral operators are related. So if you have two piecewise linear functions, you are evaluating the integral operator at the node. The two functions are the same, and one is above the other. The second differences are order. And that's why you get an order for the integral operator. The same happens with the Laplacian, provided we have weakly acute meshes. This here is what I mean by that. That is a condition on the structure of a mesh. This is a serious restriction, not so much in 2D, but in higher dimensions. And that implies monotonicity of the Laplacian, and putting it together, you have monotonicity of the full operator, the sum of the discrete Laplacian and the integral operator. I want to mention one thing here, which I think is useful to comment. This monotonicity for the Laplacian has to do with the Laplacian itself. The matrix A doesn't enter here. The matrix A is buried into I, epsilon. So the matrix A can be anisotropic. If you want, for a problem in divergence form, anisotropic, to have this maximum principle, you have to have a very distorted mesh that accounts for the matrix A. This is here buried into the I epsilon. But this is not a free lunch, okay? If you have a matrix that is very anisotropic, we don't have a ball centered at xi where we do the averaging. We have an ellipsoid. And the ellipsoid can be very elongated. Okay? It's the second scale that takes the epsilon that takes care of anisotropies. The first scale takes care of the Laplacian, and so the mesh is unrelated to A. And this is an advantage of the method. Okay. Now I want to talk about consistency. Well, I'm going to use UG, which is the Galerkin projection, to compare, to get an error estimate. So instead of U, I'm not going to use the interpolant of U, because the interpolant of U doesn't have good differential properties. The Galerkin projection does. So UG is a Galerkin projection. This is an error estimate that comes from finite element literature. So now if I look at the delta operator and I replace U by UG, I'm perturbing by this amount. All the terms, and it's obvious that I get this. Remember, the delta is a second difference, but I'm not dividing by the length. Okay? When I divide by the length, I'm inside the operator, and that's why I get this term when I'm dealing with the integral operator. And in order to get an estimate that is correct, I had to account, I told you, for what happens at the boundary layer. At the boundary layer, and you see the effect now, when I'm reducing the ball because I'm getting close to the boundary, epsilon becomes h. If epsilon becomes h, this term becomes 1. And then I have no consistency error. The error is order 1. I'm dead. I'm going to compensate with the boundary layer function, which I'm not describing to you, that is going to help me. And the reason it's going to help me is because even though I have no control of the truncation error, is order 1, I have something that I can use. When I'm close to the boundary, I have the Dirichlet value. I know that I start right. I know the Dirichlet value. The only thing I need to know is that I don't go too far. But I don't have to go inside the domain. I only have to move a distance epsilon. And this is going to be taken care of by this function. Okay? So that's the reason why, even though I have a boundary layer effect, I can deal with it. Okay. This is the consistency that we know for the discrete Laplacian. In fact, this is an important step. And this is the consistency for the whole operator, once I put them together. Okay. Then, by doing this, I can get a consistency. You see, the operator applied to the discrete solution minus the Galerkin projection minus a correction term has this form, where the epsilon to the alpha has to do with the regularity of the function, depending on where I am. Or if I have one more regularity, there will be 1 plus alpha. And the other term has to do with this integral operator. And notice that I'm dealing with the boundary, I'm putting it inside here. Okay? So this result will give me no information near the boundary unless I can deal with the boundary layer. Okay. Now why this works? And here is where the Alexandrov estimate comes in. There is something that is called the Alexandroff-Bakelman-Pucci estimate, which gives you, again, how far can you go down for a solution of a problem like this, in terms of the, remember, Alexandrov said in terms of the sub-differential of the convex envelope. But that has to do only where the convex envelope touches the function, and when they touch, I know that the function satisfies an equation, satisfies this equation, so I can replace the sub-differential of a convex envelope by the right-hand side, and that's what is written here. That's the Alexandrov-Bakelman-Pucci estimate. This is well known, again, in the theory of equations in fully nonlinear equations. And because this is true, and because we have a discrete Alexandrov estimate, we can do the same discretely. And this is what you see here. UH is going to be our solution, maybe a sub-solution, actually a super solution, according to the signs that I use. So the amount, how much the function can go down, is replaced by a discrete version of that. So I'm taking the values of Fi at each node, which are means. I multiply by the area of the star, of the patch. That would be this integral. And I add over all the nodes that are in the contact set. So that's the discrete version. This has to be proved. Okay, but that's the result. Okay. And here is proof. It's not complicated. I will omit it. If somebody is interested, maybe this is the proof, but I'll skip it. So why we have pointwise estimates? Well, I mentioned before that we have this relation for this function. Okay? So we have this right-hand side. This is our f in the previous estimate here. Okay? So if I use the discrete ABP estimate, I can get an estimate for this quantity in terms of the right-hand side. This is what I just mentioned to you. To get what I have here, I need to control the boundary layer. And if I do that, this is something I'm omitting because it's technical, I get an estimate for the first two terms. And the boundary layer happens to be within this order, so I get that estimate. That's the whole thing. This is technical, as you see, it depends on alpha. But if you look at this estimate and you take the most advantageous regularity, we get basically a linear order of convergence, provided epsilon and h are related like this. So this is interesting. So let me make a comment. So I remember I have two scales. I have the mesh size and I have a larger scale epsilon. In the best case, if the scale epsilon is the square root of h, which is much bigger than h, okay, then the method converges with linear order. And it's natural to expect that because you see, basically that corresponds to having here alpha equal to 2. If this is alpha is equal to 2 and alpha is the square root of h, I cannot have better than h. In fact, this is the optimal result that you can get. So this method is first order. So you may say, well, but I'm dealing with piecewise linears, I'm losing something. Yes, I don't get second order, but I'm dealing with a problem that I have no idea how to deal with otherwise. Okay, I'm introducing another scale that allows me to deal with anisotropies and so on, and I pay for that. I pay a reduced order. And I cannot do better. This is the optimal value. And this is confirmed by experiments. So here you have an experiment with an anisotropic A. This looks innocent, but the ratio between eigenvalues is 1 to 5. If you do that with finite element, you will get a very distorted mesh. Here we are dealing with a simple mesh, we get order 1. The relation is like I anticipate epsilon square root of h. And you can do other things. Now you can deal with discontinuous A. Now I'm really playing with fire. And the rates are more or less what you expect from theory, but we get better rates if we take different relation between the parameters that we cannot explain necessarily. So this is the theoretical result. And we can even take A's that are that are certainly not much more than C alpha. Here you have a specific form. And again, we get a confirmation of the theoretical results. Okay, the rates are very strange, 0.32 here. But this is what you expect for the alpha that we chose. Okay. So I had to stop at 45. 10 minutes. Okay, so I had to speed up. So I'm going to describe the next two methods for the next two equations, Monge-Ampere, Convex Envelope, quite quickly. So here is the equation. Remember that I want to design a method for the determinant of the Hessian equal a function. And here is the key idea. If you have if you have a matrix A, semi-definite with eigenvalues lambda 1 to lambda d, non-negative, you can write the determinant as a product of the eigenvalues. And that can be written as a mean of this quadratic form. You multiply A by Vj, Vj transpose, multiply J1 to D, and these Vj's happen to be perpendicular from each other. Okay, so I'm defining this set S perp, which are collections of D vectors that are mutually perpendicular and of length 1. If I'm able to do the mean, this is the determinant. That's a formula. Okay. So what I'm going to do is to replace this here, which are directional second derivatives in the direction Vj, by center differences. Okay, exactly what I did before. I'm using a scale which I call delta now. It's delta scale. So I go from the point at distance delta. The v has length 1, so this is an approximation of the directional derivative. And I replace this here by this mean where the directional derivatives are replaced by directional second differences. So I introduce a second scale. Well, actually here is only the first scale. I didn't introduce h. H will be the mesh. Okay, so that's the way I'm going to approximate the determinant of the Hessian. Okay, this is related to a method introduced by Froese and Oberman a few years ago in the context of finite differences using wire stencils. So it's probably better to look at this picture. You have a structure mesh, and then you want to look at certain directions that are related to the mesh. So we know how to move left, right, up, down, but when you start looking at angles, then it becomes complicated. If you want to have many angles, then you have to go farther and farther from the point. And that's the reason this is called wire stencil. You can imagine that you are in the center of the domain and you can easily get to the boundary. And if you are close to the boundary, then you need to do some magic. So this is the so-called wire stencil. Is well known. It's used by people in finite differences. So the idea was to do something along these lines within the finite element context. And the key idea is the following. Here in finite difference, people have nodal values. They don't have functions. We do have functions in finite elements. We have piecewise linear functions. So if I'm sitting at a node and I have a piecewise linear function, I can look in any direction because the function is defined. I just go away delta and I evaluate it. Well, it may not be a node. Bad luck. Who cares? It's a value of the function. Okay, so in this formula here, now I'm going to have piecewise linear functions. I'm going to go away at distance delta and I'm going to evaluate. And that's a method. Okay, that's what is written here. Well, I had to do something. I cannot take all possible directions because it's not practical, so I had to somehow discretize the sphere. I call it S per theta, so I have a resolution, an angle resolution. Okay, and then I cook up the method, which is written here. There is a plus. That means I only take the positive part of the second differences that had to do with monotonicity. And that's the method, okay? This is the method to compute the approximation of the Monge-Ampere equation. Okay, this method has some properties. Well, it satisfies the discrete comparison principle. So if you have functions that are in order on the boundary, the operators are ordered, then the functions are ordered everywhere. We have operator consistency, very much Taylor formula, because this quantity here is very much related to this quantity here. It's an approximation. So you Taylor formula and you get what I just wrote. This thing here. But the key thing is that in contrast to finite difference, I had two well-defined scales. There is a separation scale. I have H and I have an additional larger scale. And I haven't told you yet what delta is. You see delta appears in the denominator and there. Then I need to do an optimization. But that I do at the end. I don't decide ahead of time what delta is. Very much like I did in the previous example. Okay. Now, this is a nonlinear problem as opposed to the previous one, which was linear, so it's not clear that we can get an error estimate. And so I want to show you why this is doable, It has to do with this continuous dependence at the continuous level. So you have two functions, u1 and u2. They satisfy Monge-Ampere, 0 at the boundary. Then you get that the determinant of the Hessian of a convex envelope, okay, of the difference, is controlled by 0 when they coincide, actually, or by the difference of the right-hand sides in the contact set. This is a very important estimate for the continuous problem. There is no discretization here. And this is true because, well, here you have a proof. It has to do with Alexandrov estimate, and it has to do with this property, which is, I call, concavity of the determinant. When you put it together and use Alexandrov estimate, and you get this, which is basically what I claim. This has to be true at the discrete level. Why is this possible at the discrete level? Well, I already have a discrete Alexandrov estimate, which is written, it's a variation of this, and I need somehow to fill in here the argument. So here is the result. This is the discrete form of the estimate. Okay, I'm replacing this integral by a sum over nodes on the contact set, and the ingredients to prove this are the discrete Alexandrov, an estimate of the sub-differential that has to be done for this method, and a concavity, this property that has to do with the determinant I need for the discrete operator. These things have to be proved. Once you have this, we get error estimates of various types, assuming Helder regularity, Sobolev regularity, or even for discontinuous Hessians. There are various types of estimates. To digest this is certainly not the right moment. And here there are some results, computational results, that are better than what we can prove. We get linear rates. We don't have linear rates theoretically, but we get linear rates, like as I show you for the previous problem. Okay? In two instances, this is a smooth example, this is a degenerate example. And I'm about to have to finish. So let me say a couple of words about the last example, which is the obstacle problem. You see it here again. And for this problem, we have, this is at the PDE level, we have a comparison principle, and we have uniqueness by comparison principle. So I need to reproduce this at the discrete level. The main thing is that there is this continuous dependence now. It's a very simple continuous dependence. And I'm after that at the discrete level. So let me conclude by showing you what the operator looks like. Again, I do a second difference, center second difference, to approximate the Hessian. I need to compute the smallest eigenvalue. And the discretization I do as I mentioned before. So this is the discrete problem. I'm computed at nodes, this max. And for this, maybe let me jump on all of the theory that can be proved. We have not only convergence, we have pointwise estimates, and the results are again here. The structure of the estimate should be familiar to you. It's very much what I said before. Delta is the scale, theta is the angle resolution, and you see an estimate for the max norm in terms of various regularities. The convergence rate happens to be linear in the best case, and this is very much like in the first example, cannot be improved. Okay, so this is a proof that I omit for you, and here are the conclusions. So there are a few things that I wanted to show you. One is the discrete Alexandrov estimate, which I think has a merit and interest in itself, and I use it in two instances to prove error estimates for the elliptic equations in non-divergence form and for Monge-Ampere. And I also show you how to compute convex envelopes using, again, these ideas of two scales. Thank you.